me see. All right, I think this one is too big. Yes, I need this. So we have looked at butorphanol, and we are saying those are the morphinans, and now from the morphinans, so we are moving on. So we have looked at the first category, which was, you can say they were the pure analogs. Now we are looking at the derivatives or pure analogs, but they are, like, as we move on, they will be proper derivatives because they are really not analogs. They don't look, analogs would look like the original molecule. Like the morphinans, we can still call them analogs because even the numbering is very similar. When we go to the benzomorphans, now you will notice again with the benzomorphans, we remove ring C completely. So now we will have removed ring E, we will have removed ring C. So remember, initially we had 5 rings. Now we have been left with 3 rings. So in the benzomorphans, we have 3 rings. In the morphinans, we have 4 rings because we only removed ring E. So now when you look at the benzomorphans, we have removed 2 rings. And therefore, from the pentacyclic, now we are having a tricyclic, where you can still see our aromatic ring is there. This is our ring B here, definitely. And this is our piperidine ring there. So we have ring 1, A. This was still our B. This was our D, but now is our C. I hope that is clear. But do remember, at this position here, and this position here is where we had our ring C. That is where we had our ring C. And therefore, when we look at the substituents, when we look at this ring, this R2 position, or this group at that position, and that group at that position, we can call them like the remnants of ring C. I hope that is clear. That if you draw your morphine molecule, you will see the ring C will project from here and there. And of course, to completion here, remember, here is where we had like that. And then now our ring C will project from there to give our complete, of course, here we have our oxygen there to get our complete morphine molecule. So all we are saying is that the R1, which is left here as a substituent, and the R2 are remnants, this group here, and that one. And usually we can call them remnants or vestiges of the ring C. They are like all that is left of ring C. So you do not completely remove ring C. At least you do leave substituents which are the ones that are representing our 2 rings. So most important here again, we have 3 rings. We have lost ring C, but in place of the ring C, we have substituents at, of course, the points where the ring C was attached. Now in this molecule, even the numbering changes. We cannot be able to number it the same way. So the benzomorphans are also similar in structure to the morphine analogs. So we cannot, that's what I'm saying, we cannot really call them the analogs because they are really derivatives now. They have been derived from morphine by losing some of the groups, but lack ring C and E rings found in the naturally occurring opioids. That is their general structure. And of course, we are saying at that position, again, you can have a substituent. At this position there, you can have a substituent. At that position, a substituent. And again, our tertiary nitrogen, not touched. Our piperidine ring still not touched. Our benzene ring still completely intact. Now, they are pure synthetic. So again, they will be synthesizing as a racemic mixture. So the numbering, as I have said, changes completely from that of the 4,5 epoxymorphinans and morphinans. Epoxymorphinans, which are the morphine and analogs, and the morphinans. But of importance to note is what we said, that the carbon alpha to the nitrogen must you carry the R orientation. The only difference is that carbon will not carry number 9. It will be actually a carbon number 1. So when we come to number, the ring, the benzene ring, we start from here. You can see quite a difference. Now we start from here and we give that 1 prime, 2 prime, 3 prime, 4 prime. So we are starting from the benzene ring. And the positions on the benzene ring are numbered as prime positions. Now, the ring, which now is numbered from position 1, not complete numbering is done, is actually the pyridine ring. Just 1 minute. As you look at the structure, please. Hello? Morning. Yeah? Or growing supervision. Okay, we have a meeting. I think there's a school board meeting at 2 o'clock. So what we can do, I don't know when it will end. I think we can push it tomorrow. But because I don't know what time, because it's a board meeting, I don't know how long it will take. Yes, but I'll make sure that we do it before the end of tomorrow, before the end of the week. So have you communicated with all the other students? And you have created a common email? Yes, you need to create a common email where I would request each and everybody to give me a brief of what they have done. You can tell the other students. Yes, you create a common email and everybody to give me a brief. A brief report, yeah. You type a brief report of what at least you send me a brief report so that I can load it on. Because I still do not know how to make you so you send me a brief report on my email of what you have done in Benmed. What have you learned? What are the challenges? Right? Yes, so you can tell the others that. Just a very brief report, yeah, of what you have learned, the challenges that you have encountered, and of course how whatever you saw practically. Is there a relationship what we are doing in theory? What's the comparison of the practical bit and the theory bit? Yes, do you think there is a shortfall in the theory? The theory we are teaching you, what to do. It's you students who help us in changing our curriculum. What would be your input? If you ask today, what would you request? Is there anything you'd want us to add in our curriculum? Just that, just a few things, and then I believe by tomorrow you'd have done it today, but we have that board meeting. So you are 4 of you. We are 3. Make sure you communicate with all the others. You have understood what I need, a brief report, yeah, of what you have learned and your findings, challenges. Yes, and what would you, is there any additional input you'd ask for in our theory teaching? My JCLYN. Yes. Okay, thank you. Okay. I was still talking to one of us. So if you look and I'd ask you to be looking at the numbering. So if you look at the pyridine ring, the previous carbon number 9, which is alpha, to carbon number 17. You see, this was our previous carbon number 9. You remember that. This is our previous carbon number 9. This was our previous carbon number 14. This was our previous carbon number 13. So our previous carbon number 9 is given position number 1. Then again, you do not go clockwise kama kawaida. Actually, we are going anti-clockwise. You are going anti-clockwise on the piperidine ring. So carbon number 9 becomes carbon number 1, the tertiary nitrogen number 2, number 3, number 4, and number 5. And of course, now, if you look at the piperidine ring, it is fully numbered. So that's it. So, no, sorry, the piperidine ring, this position definitely hasn't been numbered, but we don't go backwards that way. So we come now we go clockwise. So we have number 1, number 2, number 3, number 4, at position number 5, which is our previous position number 13. We now go clockwise, go to position number 6, position number 7, position number 8, and then now we jump to position number 14, and it becomes our number 9. So we are saying the numbering is very different, and our substituents are now at position number 5, which was 13.9. So 5.9, very important now. And those are where you have our substituents, which are remnants of the rings, our previous ring C. So even the rings change. Our aromatic ring is A, our second ring is B. That still doesn't change. What changes is our ring D becoming our ring C. So that is important for us to note. That the numbering, you must master that numbering, because if you are going to discuss the SAR, the structure activity relationship, you must mention positions. So you must know that for the benzomorphans or benzomorphinans, for the benzomorphans, the numbering changes. For the morphinans and the 4,5 epoxy morphinans, the numbering is retained. Then we are saying that the effects on binding the receptor on the 2' position and subsequent modification are the same as in morphine. So here, if you look at the 2' position, our 2' position is equivalent to the 3 position of morphine. So we are only saying if you change that group, you make it a methoxy group, you make it an acetyl group, the influence on the binding affinity or the influence of the pharmacological activity will follow the influence as for morphine. So in the SAR of the 3 and 2', there is similarity. They also binding at position number 2 is also similar as what is found in morphine, the N substituent, which this time, as you can see clearly, is position number 2. So the difference, whatever you do here, the changes you do here and the changes you do here will follow the same characteristics as the changes you do in morphine. So again, that makes it easier for us because the SAR is very similar, but there is a slight difference that unlike previous series where the dextroisomer retains analgesic, like a previous series, the dextroisomer retains analgesic activity, but the levoisomer is still more potent. So remember, we did mention dextromethorphan, no analgesic activity, antitussive activity. So we are saying here the dextroisomer of the benzomorphans still has analgesic activity, but the levoisomer still carries the day, still has much higher activity. The levoisomers again have the R configuration at carbon 1, and the carbon 1 is alpha to the nitrogen. So that again is retained. So the carbon 9, it was previous carbon 9 in morphine, it was also previously carbon 9 in the morphinans. That position still has to carry the R configuration. Of course, in the benzomorphans, it is carrying position number 1. The R2 and R3 are essential for mu receptor affinity. We are going to look at their stereochemistry, because if you look at those positions now, if you look at these R3, where they are joined at position 5, that carbon, which is our carbon 13, still retains chirality. So this position still retains chirality, that position still retains chirality, but you can see now what we have is substituents. And because they are joined in that position, these substituents can rotate and can either face down, or this substituent can also carry the horizontal. That when it comes this way is the horizontal. When it comes this way, it is the axial. Please note, sometimes you spell the word axial wrongly. Axial. I. And L. That's the spelling of axial. A-X-I-A-L. Axial, meaning the axial is the vertical. So we are saying this group here can either, these R2, can either carry the horizontal orientation, or it can carry the axial or vertical orientation. This group here also can carry the horizontal, can carry either the horizontal or the axial being the one, sorry, the axial, which is a vertical, and the axial being the vertical, and the horizontal being, of course, the horizontal. So it can carry either of those, and we are going to look at that stereochemistry. The SAR follows the same pattern as the morphinans, and of course, if it follows the same pattern as the morphinans, it means it also follows the same patterns as the morphine and its analogs. The nitrosubstituent R3, again, follows the same rules, as we have said, as the morphinans and the morphines. We have just given it R3, I believe. I think where we are here. I don't know why we are calling it as here. I should have changed. Let's just say the nitrosubstituent R3 follows, because we are calling it R3 because we are saying the other substituents R1, R2 follows. So it depends. It can be R1. It depends on how you number them. As long as you keep checking. If you call it NR1, where the other one will be R2, R3. So when you are, of course, discussing, make sure you retain the same numbering. The nitrogen substituent R3 follows the same rules. Follows the same rules as the morphinans and the morphines. So the same rules are followed. However, antagonist substituent produce analogs with a higher agonist-antagonist ratio. So we are only saying when you have the antagonist substituents, they have a higher agonist-antagonist. So the ratio of agonist to antagonist activity is much higher compared to the other drugs. So when you have an antagonist, and like we're going to look at the antagonists, you find that their ratio of agonist activity is much higher than their antagonist activity. R1 and R2 substituents must be present to supply, we are calling them vestiges or the remnants of the C ring. That is where C ring, carbon 13-14, that is a position where the C ring had come from. I think now we have said it is position number 5 and number 9, if I'm not wrong. Position number 5 and position number 9. And we did mention that those substituents are important for agonist, or for this molecule to bind the receptor. R1 and R2 are usually methyl groups or a similar lower alkyl group. So we are saying those two groups can either be methyl group or a similar lower group. I don't even know which other lower group can be, lower alkyl group, but they are usually methyl groups for maximum activity. Of course, when you make them bigger, you introduce steric hydrons more often than not. You make them bigger, you introduce steric hydrons, that molecule will not be able to access the receptor. It will not be able to get to the receptor because of the steric hydrons. R2 must be alpha or down, since the benzene is beta or up for the analog to have agonist activity. All we are saying is that this please note, I've started with R1, R2, R3. And I think in the one I'm discussing, I've started with R3, then I've given, I think R2 and R1, but as long as you see them in here. So we are saying this is a group, which is this R3 here, is the one which is closest to the benzene ring. When we come, normally the benzene ring usually takes the vertical or the axial. Benzene. So we are saying the benzene ring, also the benzene ring has taken the horizontal, sorry. It has taken the horizontal because we are saying this has two rigid structure. So this has taken the horizontal. So we are saying then this must go down. So the position R3, the substituent has to always face downwards, and that's what they're saying, downwards here. And when we talk about the downwards is what we are calling the alpha. So this substituent here must always face down. It cannot be able to face up, because if it faces the up, we are saying this benzene ring usually faces the up orientation. So if this substituent goes to up and this is going to up, there will be interaction, because you will have the bigger groups, those two big groups, where those two groups will be facing the same side. You will have cis. You will they'll be facing the same side, and once the two big groups face the same side, there will be a lot of interference in binding the receptor. So we are only saying, because under normal circumstances this group faces up, this group here will face down, and when it faces down, I believe that's what we are calling the alpha. Then this group at position number 9, quite far from the benzene ring, it has the freedom to either be horizontal or go down. It can either be horizontal or go down. When of course it goes down, it's the alpha. When it goes this side, it is the beta. So that's what we're saying. That's why I said that the orientation of those groups is very, very important. So let us look at them again. R2 must be alpha, as we have said, going down. Since the benzene is beta, going up. So please note, up, horizontal, vertical. We are considering vertical to be beta. We are considering, so not, yeah, we are not vertical, sorry. We are considered, we are here, it's a substituent, we are considering it going, if it is facing upwards, going up is beta. If it goes down, it is alpha. So remember, all we are saying is that when it goes up, it's going away from you. When it comes down, it's coming towards you. So these are a bit different. So this alpha, it's the same, that alpha coming down, coming towards you, alpha, and when it goes up, going away from you is beta. And all we are saying is that this substituent that is at position number 5 must always carry a down orientation or an alpha orientation, because for maximum activity, the benzene ring should have an up orientation. So you cannot have both of them carrying the up orientation for the analog to have agonist activity. R1, which is at position number 9, can either go down, and going down, which also is Cs, going down, which is Cs, or it can go down, which also is the same, is alpha, can go down, which is alpha. So this, I think we should have put alpha here, which is alpha, producing analogs with activity about equal to morphine, or it can go beta, which is up, also trans. So here it's down, Cs, up, trans, producing agents 4 to 30 times as active as morphine. So we are saying R1 can either be alpha going down. If it goes down, it means that group is not going on the same side as. If it goes down, we are calling it Cs. It means it will be going down. It will be facing the same direction as the group at position number 5. Remember, we have said the substituent at number 5 must always face down, because the benzene group faces up. So the substituent at position number 9, surely, if it also faces down, it will mean the substituent at position 9 and the substituent at position 5 are facing the same direction, and therefore that is our cis isomer. Cis isomer is when those two groups are facing the same direction. Hope that is clear. If the substituent at position 9, because it's the only one which can either be down or up, faces up, then the substituent at position number 9 will be facing a different direction as the substituent at position number 5. And because the two substituents are facing different direction, that is a trans. So I hope you can understand. There is alpha, which is down. There is beta, which is up. There is also cis for the two groups. Cis and trans, you are looking at the two substituents at position 5 and at position number 9. If both of them are facing the same direction, for sure that is cis. If both of them are facing different direction, that is trans. When any of those substituents is facing down, we say that is alpha. If it is facing up, we say that is beta. I hope that is clear. And when you have the substituent at position number 9 carrying the alpha orientation, or when you have the cis conformer, then you have that resultant benzomorphan has lower analgesic activity than when the substituent at position number 9 is having the beta orientation. I'll repeat again. When the substituent, remember we have said the substituent at position number 5 has no choice. It always must have the alpha orientation down because the benzene is facing up. So it does not have a choice. It must always carry the alpha orientation. The substituent at position number 9 has the freedom because it's much further. It has the freedom. It can either face up or down. When it faces up, it means actually all of them. When it faces up, it means that substituent, when it's facing up, compared to the substituent at position number 5, they are on different directions. And that is a trans, which we are calling the beta. If it faces down, it means that substituent at position 9 and the substituent at position number 5 are facing the same direction. That is what we are calling the cis. And the cis has lesser analgesic activity than the trans. But because it has lesser analgesic activity than the trans, it will also have lesser abuse potential. So although it is a weaker analgesic, you use it clinically as opposed to using the beta or as opposed to using the trans conformer because of lesser toxicity. I hope that is clear now. So we are saying R1 can be alpha down, which means if R1 is down, R2 is also down. That is correct, actually, cis. But first I would have said, yes, that's correct, cis, producing analogs with activity about equal to morphine, or it can go up, or what we are calling trans, producing agents 4 to 30 times as active as morphine. The beta agents will support narcotic analgesic, or they will have the toxic liabilities, all of them, while the alpha series will not. And R4 must always be either a methoxy group or a hydroxy group. Of course, when it's a hydroxy group, there definitely will be more analgesic activity. As we have said as earlier, we have said the SAR is the same than when it is a methoxy group. So that is the SAR. The vestiges, those two groups which are remnants, depending on which one you're calling in, what is important to note is the group at position 5 and the group at position 9 vary. Their stereochemistry, very important. That at position 5 must always be down the alpha. That at position number 9 can either take alpha or beta. Now, when it takes the alpha, you will get cis. And when you get the cis, this is not the best conformer because of course, steric hydrons. It does not bind the receptor as strongly as the trans isomer. But of course, the better the binding, the higher the toxicity, the higher the toxicity, and therefore, clinically, you will go for that. Clinically, you go for the drug that has good activity because the alpha isomer, that alpha isomer still has higher analgesic activity than morphine. So you will go for it because of the lesser toxicity. Alpha isomers are superimposable on morphine, but have a higher mu affinity than morphine. And therefore, we are saying when it comes to analgesic activity, the beta is greater than the alpha, which is greater than morphine. So the beta is greater than the alpha, which is greater than the morphine, but now the beta has a maximum toxicity, so you go for the alpha. In cases of people, of course, patients who have a lot of pain. The alpha and beta isomers also have higher lipid water partition coefficient compared to morphine. Again, remember, you have removed the ether linkage. You have removed the hydroxyl group at position number 6. So these drugs have slightly higher lipid water partition coefficient because you have said because of their shape and steric hindrance. You see, you have removed a portion of the C. So this molecule is not as bulky as the morphines and analogs, and therefore it can get into the receptor much better, access the receptor more effectively, bind the receptor more strongly, and therefore give you better activity than morphine, and at the same time also found to have quite low toxicity, and therefore clinically it is indeed the preferred isomer. The weak alpha isomers are preferred clinically due to their lower dependence liabilities. I hope that is clear. And again, these are now compounds. You can see here we have used the I've said this is R here and R1. So this we have already said it must be always be a hydroxyl group. From our SAR, we have said it is usually a hydroxyl group or methoxyl group. So for these drugs, it is a hydroxyl group. Now the group that is changing is the group at R1. So this group here definitely is changing. It's the R group changing. That group here is changing. That group is changing, and also these two groups can change. These two groups can change and to give us a different compound. So we have the pentazosine, and when you look at pentazosine, you can see it from the name penta, it gives you 5, and you can see at position up here, it has 1 CH, it's an allyl group, but 1, 2, 3, 4, 5. That's why we are calling it pentazosine, and at this position, it has a methyl group, and I believe even at that position, it has a methyl group. Remember, we did mention preferably those groups are methyl groups. Phenazosine, remember we did mention, even when we were looking at the morphine, we did mention that the R group, this group here, can be phenethyl group. And when you make it phenethyl group, remember, we say to increase agonist activity. Remember, we said beyond, incidentally for these drugs, beyond 5 carbon atoms, between 3 and 5, you have antagonist activity increasing as we increase the number, decreasing as we increase the number of carbon atoms to a maximum of 5. Beyond 5, like when you have the phen, this is a phenyl group, phenethyl group, then you find that again that drug now becomes an agonist. Pentazosine is an antagonist. This becomes a good agonist. So I think even you can be able to look at their structure so that you can understand what we're talking about. So again, remember, we say that is position 1 there, position 1, position 2, position 3, position 4, position 5. Then we go anti-clockwise, 6, 7, 8, and these are position 9. So very important positions are that one 9, and this one here, position 5. Please note that the numbering starting from the previous carbon 9 becoming 1, 2, 3, 4, 5. Go clockwise. Just remember at 5, go clockwise, 6, 7, 8, and then you get your position 9 there. And of course, at this position 1 prime, 2 prime, 3 prime, 4 prime, as we had already said. So when we look at metazosine, we are saying normally the best group at this position, and as you see most of the compounds, the best group at this position is usually a methyl group. So at that position 5 and 9, methyl group is the best group, minimal steric hydrons, and remembering this will take an alpha orientation, and that will also, that's also taking a down orientation to minimize toxicity. But of course, it does not have maximum analgesic activity, but because of the reduction in toxicity, then you prefer that group. So that is what we're calling metazosine. That is metazosine. Then you have phentazosine, and you can see this group here. That is our phenyl group, 2 carbon atoms. That's phen-ethyl group there. And the other groups are the same. You say this position, and you can see in all of them, you retain a hydroxyl group for maximum activity. So the only difference here is this group which is changing there. And then you have the pentazosine. The same case applies. Again, it's at the nitrogen that you're changing, and you can see you have you have actually you can call it this pentene. You have a branch pentene ring or methyl butene ring, because you see 1, 2, 3, 4, and of course that methyl butene ring at that position. Again, we are considering to be pentazosine because they are just counting 1, 2, 3, 4, 5 to make it easier. And it's an allyl substituent, so that I would expect it to give us antagonist activity. Then you have pentazosine, again retaining the same methyl groups at that position. All that has happened is that our position, again, remember, I normally don't cram because it's just best to remember them. That is position, this I think was our position 1, 2, 3, 4, 5, 6, 7, 8. I think this is our position 8. Position 1, this was our position 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this is our position 8. Sometimes cramming all these things will be a challenge, so it's good to be able to derive them. So you remember, you see, when you see pentazosine, the only difference is that there is a ketone at position number 8 of ring B. That's the only difference. And of course, it also has a cyclopropyl methyl, and also in cyclazazine also has a cyclomethyl, but in cyclazazine it does not have the ketone. So you can also see that they give them names that can almost help you remember the structure, because you see the cycler there, you know there is a cyclo. You see the ket there, you know there is a ketone. The met there, everything is a methyl. 1, 2, 3 for metazosine, methyl, methyl, methyl. Then phentazosine, there is a phenyl group. Pentazosine, there is a there is the pentane derivative, or of course the pentene derivative. So the names, you can remember the names, they have some link to the structure. The name has a link to the structure, and you can see the major change, as exception of pentazosine, the major change is only at position number 2. Major change is only at position number 2, the exception, of course, of pentazosine. The others, those positions, the structure remains the same. And we can note metazosine is a prototype, and we have said the metazosine. I think it's already time, so let us finish this. Should have told me it's time. Metazosine is a prototype, and we have said metazosine, the M tells us 3 position, nitrogen position, position 9, position 5, all of them have a methyl group. Is a prototype with a higher lipid water partition coefficient than morphine. Cyclazosine, which has a methyl cyclopropyl, again from the name, is a potent mixed agonist antagonist. But remember, we did mention that this class of drugs, the agonist-antagonist ratio is much higher. It has a high lipid water partition coefficient, but also just like the other one we mentioned under the benzocyclophan, which was a morphinan, which was we said was also is actually this drug is also a cyclophan, and even the cyclazazine are also hallucinogenic. Remember, we also mentioned cyclophan, which is a morphinan, we also said is hallucinogenic. So also this was found to be hallucinogenic. The phenazozine, this will have, as we have said, the phen-methyl group is a mu agonist and is more potent than morphine due to the phen-ethyl group. Remember, we did mention that group is more than 5 carbon atoms. Then again, there is increase in agonist activity, and that agonist activity is in this new site. Remember the site I showed you, site A, which is on one of the farthest ends. So when you have introduced that phenyl ring, CH2 phenyl ring, that phenyl ring is able to interact with site A. So it's not an interaction with the other sites where we had the other sites were D, C, and B. It is interacting with the extra site which we showed on the morphine receptor, and therefore giving us better activity. The molecule, of course, you have added a phen-ethyl group, much higher lipid solubility, much higher rate of penetration of the lipid membranes, and of course giving us very good activity. Ketazosine was also found to have very high affinity for the kappa receptors, and indeed the kappa's name is said to origin from the ketazosine. So ketazosine was also found to have very good high affinity for kappa receptors. So you find that these are drugs that will have a lot of, they will also, because of their very high potency, they will also have a lot of abuse potential liabilities, and therefore are not drugs, are drugs that must be given if they have to be given in a hospital setup because of their liabilities. I think that is the end of the third group now. We have done 4,5 epoxymorphinans and the analogs. In fact, it's almost the fourth group because we started with morphine, and then we looked at the analogs where we were talking about the cordones, hydromorphones, and then we went from there. Now we have looked at the morphinans, where we have looked at the levophanos and the valofans, and so on. And we have been able to look at the benzomorphans and the benzomorphans. That's where we are looking at the pentazosines, the metazosines. So that's actually, we have looked at about 4 groups. So we still have another, I think, 2, the 4-phenyl, I think we have about 2 4-phenyl piperidines, the anilidopiperidines, and the proper, about 3 more groups, and we'll be done with the narcotic analgesics, because and unfortunately the other groups are not as lengthy as what we have already covered, and we do need to finish because they have this unit is highly loaded. Sometimes you cannot understand. I was hoping that once, because we are doing curriculum review, that they would be able to adjust the unit a bit, or modify it a little bit, because it's loaded in that it has subtopics that are not related to each other. That's why I can say it's a bit loaded, but I'll try the best I can. Once we finish the narcotic analgesics, the other groups are not very lengthy. So this is the unit. It is PHA 2513, pharmaceutical chemistry, I think the 19 CNS2. You can see we are looking at the narcotic analgesics. There's general anesthetics, because they're also for pain. I bet that's why they put them together. Central acting muscle relaxants, and relax muscles, and of course they must be having an element of pain. Now these ones, they have no connection, anti-Parkinsonism or anti-Parkinsonian drugs. And then also we are supposed to look at CNS stimulants and the hallucinogens. So, but fortunately, the hallucinogen, the CNS, these ones are not bigger topics. The biggest one actually is the narcotic analgesics. So once we are done with this, I want to believe 2 or so lessons or 1 lesson per each of these others, we'll be able to finish. So we really need to move a little bit fast so that we can be able to finish. So what you need to be doing, like now I've said, next time you look at the 4-phenyl piperidines, we should be look at the anilopiperidines. Anilopiperidines include the fentanyls and so on. And then there is the final one where we have the propyl derivatives, which includes things like propoxyphene. So you do need to, if you could draw the structures, look at those 4 categories, or 4 categories we are not looked at. I've said we have the 4-phenyl piperidines, where we have the methadones, we have the anhydropiperidines, which are still a subgroup of the 4-phenyl piperidines, where we have the fentanyls. Then we have the propyl derivatives, or the open chain derivatives, where we will be looking at drugs like methadone and the propoxyphene. So kindly look at this, the groups that you have not looked at. Make sure you have the structures, you draw the structures, and if you draw the structures, it will be much easier for us to finalize, because we do need to perhaps another 2 lessons, and we should finalize on the narcotic analgesics, because as I have said, we do have quite a number of subtopics which we also need to look at for us to complete this unit. We also need to start thinking. I think we need to do our cuts early. So I think I need us to start thinking. Once we finish the narcotic analgesics, we will do our first cut. So that now, because the marking and so on, it takes time, and I need to be in time. And I'm actually the examination officer, so I must make sure my results are in on time. So I would want us to do our first cut immediately we finish the narcotic analgesics. Immediately we do our first cut, because anyway, that is the biggest group, as I've said, and it is a standalone. It has its own characteristics, its own SAR, not connected to the others. Of course, even the other small groups, each group is a standalone. Its SARs are not similar to the others, but the narcotic analgesics are the largest. So please, can you continue? Start. I hope you are reading. You must be able to understand how the structural modifications are being done, starting from morphine to get the morphine analogs, to get the morphinans, to get the benzomorphins, to get the 4-phenyl piperidines, to get the anhydropiperidines, to get the open chain derivatives. You must understand those various structural modifications, and in your mind, when you look at these structures, you must continuously ask yourself, are they obeying the morphine rule? So the morphine rule must always be at your fingertips. You must be able to look at this structure and ask yourself, are they obeying the morphine rules? Is there an exception? Because we did mention that most of these compounds, even as we do structural modification, they should obey the morphine rule. And I think with that, and I can see, I don't know whether you are more than 35. I don't know whether there's any question. So kindly, as I have said, be safe. Don't leave until I save. Is this safe? Save users. As I have said, draw the structures and try to look at them and to ask yourself what has been done. As I've said, we are starting from morphine. Tunaichuja tu. Unaendelea ukichuja. Finally, unaichuja mpaka that piperidine ring. You open it up. So you tunaichuja to, you start with morphine, and initially you remove the piperidine. So you remove the ether linkage. Then from the ether linkage, you come down, you remove the C. Then from the C, the C, you remove the B. So when you remove the B, you are having phenyl piperidines, because you'll be having only 2 rings, the phenyl ring and the piperidine ring. Then again, your piperidine ring, you break it such that now they are open chain. The piperidine ring is not closed. So you're starting from morphine, going down until you get to the very simple structure. And that simple structure, we should be able to confirm whether it still follows the morphine rule, because if it follows the morphine rule, even without the extra hydrophobic areas, it is still able to bind the receptor and bind it effectively to give us analgesic activity. I think with that, we can call it a day. It on Thursday for the anti-cancer drugs. I had given you an assignment. I would wish you could hand it as early as possible, earliest possible. So as I've said, what marking usually is quite a big challenge. So that one marks as quickly as possible, early enough, entering the marks and so on, and then prepare for on both sides. Start reading, preparing for your cards. We are in 5th year. We do not need persuasion anymore. We already know why we are where we are. We have to do our cards. We have to do our assignments. We have to do our exams. We have to do our projects. Quite a lot of work.